I am Mounir Laroussi, professor at the Electrical and Computer Engineering Department of Old Dominion University, and I'm the director of the Plasma Engineering and Medicine Institute. Plasma is known as the fourth state of matter. There are three very well-known states for most people living on this planet, which is the solid, the liquid, and the gas. However, there is a fourth state, which is called the plasma state. That's when a gas becomes ionized, and most of the matter most of the visible matter in the universe is actually in the plasma state. Most people don't realize this, but plasma we use it in everyday life. Plasma is, for example, the state of the gas in neon signs, in fluorescent light tube. Plasma is used in the manufacture of semiconductor components. Plasma is used to treat the surface of material, from textile to plastics. So in reality, plasma is extremely useful state of matter that we use in industrial application, and that people just normally don't think of it, since they don't really see it directly. Energetically, plasma can be divided into two. One is the thermal plasma, or hot plasma, and the other is low temperature plasma, or non-equilibrium plasmas. Hot plasmas are actually very useful too. They are used, for example, in welding and used for energy production. Low temperature plasma are used in many industrial applications that involve, as I mentioned earlier, the manufacture of semiconductor devices, the treatment of textile or plastics. These require low temperature. So low temperature plasmas have found a lot of application, a lot of industrial applications. About maybe 20 years ago, scientists were able to produce plasma in low temperature plasma in atmospheric pressure. Before that, plasma required vacuum systems for low pressure, to establish low pressure. However, many technical ways were found where we can generate plasma, low temperature plasma at atmospheric pressure. Where one of the application was how can we use this plasma to interact with biological material and systems. The early research was for what's called sterilization or decontamination, which means killing of bacteria, and that was very successful. Low temperature plasma turned out to be a very good medium where you can kill bacteria, including bacteria that are resistant to antibiotics. So that research kind of triggered the whole interest worldwide that plasma actually can be used for biomedical applications. So it started that way, and then as research advanced and more people got interested in this, the application went to actually mammalian cells, like our human cells, and it turned out to be that the interaction of plasma with mammalian cells is quite different than it is for say bacteria. Mammalian cells are what's called eukaryotic cells. They have a different structure. The cells have completely different structure, so, and completely different response to outside stress, if you like. So it turned out to be that for low power condition, for low exposure condition, mammalian cells can survive the exposure of plasma. Unlike the bacteria, they can be killed. So the idea, of course, came around, then maybe we can apply plasma to actually living tissues, maybe to kill bacteria without affecting the cells. So mammalian cells, which is like our human cells, have a completely different structure than bacteria. Therefore, they interact in a completely different fashion when they are exposed to low temperature plasmas. Well, it turned out that if you use very low power or very short exposure time, mammalian cells can survive the exposure of plasma, but while bacteria can die. And therefore, the idea came that maybe we can use low temperature plasma to expose mammalian cells or even tissues where we can kill bacteria without negatively affecting the mammalian cells. And one direct application of that would be for wounds, so we can sterilize, decontaminate wounds, and that will help in the wound healing. However, it turned out to be it's even better than that. That under some condition, exposure to low temperature plasma, mammalian cells some mammalian cells, like cells called fibroblasts or epithelial cells, can actually proliferate, which is also which actually can help the wound to heal. So we can kill the bacteria and proliferate healthy cells. So this is a fantastic application for wound healing. Back in around 2004, 2005, we developed a device here at Old Dominion University called the plasma pencil. The plasma pencil is a device that can shoot a beam of low temperature plasma, a beam that can be up to maybe 2 to 3 inches long. And that device can be extremely useful for biomedical application. Because plasmas, when you generate them between electrode or confined inside an enclosure, it will be very hard to use them, for example, on a patient. So the idea was, can we get the plasma out into room air? We can shoot it out, so we can aim it at a tissue or cells. And so we developed this device called the plasma pencil. And the beautiful thing about the plasma pencil is it shoots a low temperature plasma jet out into the ambient air and can be aimed at a tissue, and the treatment is quite localized because it's a very thin beam of plasma. I use beam here in kind of general term, and we also tested it on fibroblast cells and epithelial cells, and we found the condition under which those cells are not damaged. Therefore, a plasma pencil is a device can be used effectively in wound healing applications. And we tried a model, multicellular organisms, and we showed that the wound on those multicellular organisms can be healed after exposure to the plasma. So that also tells us that the plasma doesn't have, under some condition, no negative effect on healthy mammalian cells. Later on, our research also got focused for a few years on dental application. I have a collaboration with the ODU Center for Dental Hygiene. I work with Gail McCombs on some projects, and it turned out to be that the plasma pencil can be also a very useful device for medical application because it can emit that thin beam of plasma that I mentioned. Therefore, you can put it into to decontaminate, sterilize a root canal, for example, kill the bacteria, the biofilm that's called plaque that builds in oral cavities and on teeth, etc. So there was a lot of interest from the dental people in the application of the low temperature plasmas, and especially here in our lab, the plasma pencil. Now our research also advanced more, and we applied a plasma pencil for cancer research. And this is a field of great interest to us. Right now, a lot of our activity is on cancer application. And so far, we showed that the application of low temperature plasma to cancer cells is very, very interesting and promising because we showed that we tried several cancer cell lines, prostate cancer, leukemia, squamous cell carcinoma, and we showed that plasma can actually destroy those cancer cells. And it also turns out that the cancer cells are a lot more susceptible to the treatment by the low temperature plasma than the healthy cells. And that's because It turns out that plasma is most effective during the replication phase of the cells. And there is during the replication phase, there is a phase called the S phase. That's when the DNA of the cells replicate, and plasma is very, very effective to kind of stop that S phase replication. So cancer cells cannot proliferate and replicate, and the healthy cells, so they somehow can adjust their metabolic behavior to stay alive after plasma treatment. So that's really a fantastic outcome, is that we can kill cancer cells, and we tried many, but yet healthy cells can kind of survive that plasma treatment.
So have you actually worked on any cancer patients?
No, the work that we did is all what's called in vitro work. We have not done any work in vivo or on people, on patients. However, there are other groups around the world that have started working on in vivo, and they showed that for, let's say, rat or mice model, that plasma can kill or reduce tumors. However, at this time of research, we don't know if the tumor will come back or not after treatment. So there might be a treatment regimen for maybe several weeks or several months of plasma treatment, and probably plasma can be used as what's called an adjuvant therapy to help, for example, surgery or drugs or something like that. So this research is ongoing in several labs. Most recently, our work has been, as I mentioned earlier, focused on cancer application. We develop several devices. Most of them are these jet devices, and we can make what's called microjet. So we can get very, very thin, several tens of micrometer diameter plasma jets for a precise and controlled application of the plasma. So that way we can treat in an accurate way without, spilling out the treatment to the surrounding tissue, for example. We also develop what's called large volume, low temperature plasmas. See, these are plasmas are not jets, but they are much bigger in volume and area, and those can be used, for example, to treat the surface of devices. We can sterilize, for example, medical tools, and treat some gears or some cloth or the surface of some materials of interest to us. One of the interesting things that we really would like to get into is treating a surface in a patterned way, and then growing the cells that we want only along the patterns. That way we can maybe create a tissue structure, which will be an artificial tissue structure. This is still research at its beginning that we are trying in our lab. Low temperature plasmas have very energetic electrons, while the heavy particles like the ions and the neutral are rather cold and low energy. So those electrons, when they collide with the background atoms and molecules, they generate what's called reactive species, like radicals, for example, atomic oxygen, or hydroxyl, OH, or maybe hydrogen peroxide if there is some water vapor in the environment. Those reactive species are the ones that actually interact with biological cells and cause, for example, oxidations, and also can trigger what's called signaling, which is signals that are transmitted chemically into cells, so they can do one thing or another. So that reactivity of the plasma, that chemical reactivity, it's what's enabling a lot of these biomedical applications. As I mentioned earlier, The biomedical application of plasma started mainly uh, uh, focused on killing bacteria and healing of wounds. However, through the years, where a lot of scientific researchers, investigators, many groups around the world in the United States, Europe, Asia, Japan, China, Korea, and all that, they got into the field, and there was basically a lot of advances and milestones of research that are being achieved almost on a yearly basis. So in the last decade, plasma has kind of advanced to a point where it's showing a lot of promise to actually being used in a certain therapy in the medical field. There is now actually a sizable research community globally that has engaged into this research. We have meetings almost on a yearly basis where we can meet in conferences to present our latest results. So we have workshops that we run. For example, the international workshop on plasma for cancer treatment. The next one will take place in Japan very soon, in a few months. So there is a whole, if you like, buzz about this research. There is a whole lot of interest and the advances that are happening on a regular base are spurring more and more research and interest in new, if you like, investigators, young investigators getting into the field, and the community growing on a constant basis.